All right, today we're going to get in on Chapter 13 in equilibrium, and there are some big major goals that we just want to make sure that we keep in play. Number one, discuss how and why a system comes to equilibrium, or how it comes to that equilibrium state, and also discuss the characteristics of equilibrium, what it means, and then finally determine how to calculate both the concentrations of reactants and products for a system that has come to rest at equilibrium. All right, now for equilibrium, the first thing we got to do is define the equilibrium condition. Some properties of a system at equilibrium: it appears from the outside to be inert or non-changing. So from the outside, you don't visibly see any changes. It can be initiated from both directions, and this is kind of that idea that in reality, when we're talking about chemical equations, we really can treat them all as being reversible. If we change the energy or we change enough of the conditions, we can force a reaction to go in the opposite direction. This is a little bit falsified in the fact that we can only study this in a closed system, which isn't necessarily realistic, other than just closing it off and running the reaction in a separate container. And we're going back to, these are all based on the ratios of reactants to products. So we're going back to just straight up coefficients of the balanced chemical reaction to dictate how we're going to look at rates on for equilibrium on these things. Okay, now equilibrium is a dynamic situation, and it may seem like no changes are occurring, but there are still some changes. And the example that I have is a car and bridge analogy. And if you think about this little island over here, each one of these X's represents a car. Okay, well, if I have 1, 2, 3, 4, 5, 6, 7 cars, all right, now they're all moving around the island, they're all driving around. If one of them leaves, all right, well, at the same time, if another car comes back on the island, I still have 7. So even though they're still moving and you can have things, go back and run a chemical reaction in a different way, you're still going to, from the outside, appear to be non-changing. So again, you get no net changes because initially or eventually the number of reactants and products becomes constant over time. So even though you may have some reactants and products going back and forth for that reaction, the net change isn't any different. Okay, now this is just a graph of the concentration versus time for a given reaction. Apparently it's really important here. Here's the reaction. You have the reactants and you have the products. Now the slopes and the shapes are equal because you'll notice that for the coefficients it's all 1. So there aren't any differences here, and essentially over time the concentration of the reactants comes down, and then once it reaches a plateau or a straight line inside equilibrium, the concentration of the products will go up. Once you reach that plateau or static equilibrium, that one stays the same as well. Okay. Now from a kinetics perspective, I know we just got done with it. From a kinetics, remember, is how fast. So for a kinetics perspective, once you reach equilibrium, okay, the reaction rates are equal to each other. Okay, so again, if these are the reaction rates over time, the reactants are going to, if this is going forward, okay, so it's going to slow down, slow down, slow down, slow down, slow down. So you reach equilibrium, reverse rate would be the same. There'd be a very small portion going backwards, and then once you get equilibrium, they are equal to each other. Okay, now here's a little bit of accept the proof here. If you think about your reaction rates, rate forward is equal to rate reversed. For a reaction AB, your K of the forward reaction, that's where the F is equal to A, the reverse is equal to B. And at equilibrium, the forward and reverse reaction occur at the same rate, or you have the rate laws equal to each other. Okay, remember, a little bit of proving the proof. Now, if we rearrange the last equation, we essentially get the forward rate, or the forward rate, or where we're generating the products, over the reverse rate, where we're regenerating the reactants. And so what we end up with is this capital K. Okay, notice we're making a switch to capital K. That's a biggie here for equilibrium. Capital K, where KEQ is what we refer to as the equilibrium constant, okay, is the products over the reactants, and we also can refer to this as KC, which is where equilibrium is expressed using molar concentrations. Okay, we're going to come up with, over the course of the next 3 chapters, 1, 2, 3, 4, about 4 capital K values, so we just need to keep those straight But anyway, Kc is what we're going to work with. Now, equilibrium position of a reaction. This is simply deciding, is it going to favor the products or the reactants? Or in other words, which way is it going to go if it's reversible? It's determined by three things: the initial concentration, the energy of the reactants or products. So this is the whole exo versus endo thing. Is it going to require energy? Is it going to lower the energy? And the degree of the organization. Because remember, we got to have collisions. And for organization, this a lot of times is just based on the fact, is it a solid, a liquid, or a gas? What state is it in? How much energy or disorder? Because the real world goal, and I know this looks contraindicating, or but to contradict each other. But remember, we know one of the goals is low energy. That makes things happy. That's why they rearrange electrons. That's why they undergo chemical bonds, etc., etc. The other goal is high disorder, and I wish we had more time to go into it, but it's just the way it is. So this is the goal of the universe, so to speak, is to lower the energy and increase the disorder. So that's why this whole degree of organization is going to come into play, which is essentially how fast are the particles moving and how much chaos is there. Now, equilibrium position. If we say it lies to the left, it means we're going to produce more products and less reactants. And if it lies to the right, it's going to produce less reactants and more products. So this is just the reactants are on the left side of the arrow, or the left side of the equation, the products are on the right. Now, if the reactants are mixed and the concentrations do not change, so they stay exactly the same, a couple things could be true. One, could already be at equilibrium, or two, the reaction rate is so slow that the change is too difficult to detect. Okay, so those are just two scenarios. If you mix two things and nothing happens, one, they could already be at equilibrium, or the reaction rate is so slow that you're not going to be able to tell the difference. Okay, let's talk about the equilibrium constant. Now, the law of mass action was created or developed by two guys who were Norwegian in 1864, Goldberg and Wage, and I'm probably totally saying that wrong, for a general reaction where the lowercase letters are the coefficients, the capital letters are the actual chemicals. The equilibrium constant, again, is Kc, so this is using molar concentrations, and the general term, or the general way that we write equilibrium constants, is where remember, the products go on top, the reactants go on the bottom. So for example, it would be C raised to whatever power that coefficient was. Concentration of D raised to the power of its coefficient. Reactants, you do exactly the same thing. Now, so again, here's a little bit more of accept the proof. So the rate forward is equal to A, and I know we're oversimplifying. This would have been if it was determined experimentally, because here we're just using the coefficients to talk about the rates. But our Kc value, this is just kind of the proof for it. Ultimately, this is what matters, is that we can write what's called this equilibrium constant. Again, if we reach equilibrium, the rates are equal. So our equilibrium constant is that concentration raised to that power, concentration raised to that power. Okay? Now, for example, okay, I already apparently had the box around that. Write the equilibrium expression for this reaction. Okay, here is going to be my equilibrium expression. And I believe that you have to jot this down. This one in the last slide as well. So if you haven't done that, make sure to write that down, where you simply have nitrogen dioxide raised to the 4th power, water raised to the 6th power, ammonia to the 4th, oxygen to the 7th. So when we're talking equilibrium expression, we can go right to the coefficients. Okay, we don't have to do the method of initial rates like we did in kinetics. Now, what would it be for the reverse reaction? It would just be the inverse. You'd flip it upside down. You'd have the ammonia and the oxygen on the top, and then you'd have the nitrogen dioxide, squeeze this in here, on the bottom. Okay, so that's the thing, is we can always flip-flop them, but you're always going to have the products on the top and the reactants on the bottom. Now, we will always have the same value. Now, let me back up for a second. With kinetics, let me come down to the bottom here. When we just got done with kinetics, it said that from kinetics, lowercase k and lowercase k, and we've just put forward and reverse rates here. They're temperature dependent. Okay, they're temperature dependent because you're going to change the rate of the number of collisions, right? If you increase number of collisions, you're going to increase how much is occurring, how much is reacting, etc., etc. So the equilibrium of a reactant Kc is also temperature dependent, primarily for the same reason. Okay, so you always will have the same value at the same temperature. No matter what amounts are added, the ratio at equilibrium will always be the same. However, if you change the temperature, you're going to change both lowercase k and capital K. Now, this is just showing you each set of equilibrium concentrations does depend on its initial concentrations. And the next PowerPoint is going to make this, I think a video is going to make this a little bit easier to follow. But if these are my initial concentrations, okay, to find my K value, all I have to do is plug those in for my these are my initial concentrations, these are my equilibrium concentrations. So my K will stay exactly the same, but my equilibrium conditions will be different depending on the concentration. So that's for right now, that's all I expect you to be able to get out of it. And then the next slide, next video, I'm going to show you how we actually figure out, when we're given initial, how we figure out equilibrium, how we solve for K, etc., etc. Okay. And if you want to look for some practice problems, go ahead and look on page 614, look at 13.2, page 617, look at 13.3. They're pretty straightforward, but they're worth a look just to make sure that you can follow them at this point.